Hey guys, so here's a conditional random field. Now, what is a conditional random field? Well, it models the probability of sequences, the probability of y given x, where y is a sequence of labels and x is a sequence of data points. So, for example, let's look at parts of speech tagging, where x is an English sentence and y is a sequence of parts of speech tags. So for example, if we have the sentence, the dog barks, the parts of speech for that sentence are determiner, noun, verb. That is, the part of speech tag for the is determiner, the part of speech tag for dog is noun, and the part of speech tag for barks is verb. And if we trained a CRF, then our CRF could output, say, a probability of 0.2 for this sequence of labels given this sentence. So a CRF gives you a probability of y given x for any xy pair. So we can ask it, what's the probability of any labeling sequence? For example, verb, determiner, noun, given the dog barks. And it'll give us a probability of 0.01, which is hopefully lower than the correct probability above of 0.2, because this parts of speech labeling is incorrect. So how does the CRF compute the probability of y given x? Well, the main thing it has is a scoring function that computes the score of an xy pair. So the higher the score, the more strongly x and y go together. And it's an unnormalized score, not a probability. So to convert that score into a probability, we compute the sum of all scores for all possible labelings of x. Then we normalize the score by that sum. So to state it compactly, to compute the probability of y given x, we first compute the score of x and y, then we normalize that score by dividing it by the sum of all scores for all possible labelings of x. So let's give an example of how a CRF would naively compute the probability of y given x with the example of determiner noun given the dog. So let's say that the only labels that we have in our label set are determiner and noun. Well, the first thing we do is compute the score of x and y, which is the dog and determiner noun. And we get a score of, say, 7. Next, we have to compute the sum of scores of all possible labelings of x. And all those possible labelings are determiner, determiner, which has a score of 1 in this case, determiner noun, which has a score of 7, the same as above, noun, noun, which has a score of 1, and noun determiner, which also has a score of 1. So we sum all those up, and we get a value of 10. The numerator is 7, and we get 0.7. So the probability of determiner noun given the dog is 0.7. This is how a CRF would naively compute the probability of y given x. So up to this point, I've been saying this is the way a CRF would naively compute the probability of y given x. Why have I been saying naively? Well, it's because to compute the probability in this way is in general intractable. Why is it intractable? Well, it's the way we're computing the denominator. Computing the denominator in this way requires us to sum over all possible labelings of x. And the number of all possible labelings of x grows exponentially with the length of the sentence. Specifically, the number of all possible labelings of x is n, the length of the sentence, to the power of the label set size. In parts of speech tagging, we can have dozens of labels, and the length of sentences can be very long. Doing a back of the envelope calculation, I looked it up, and the Stanford parser uses 36 to 45 parts of speech tags. And according to Google, the average sentence length is 15 to 20 words. So let's say we want to label a sentence with 17 words and 40 possible parts of speech tags. That would give us 40 to the 17 possible labelings of the sentence, which is a number with 27 zeros in it, which is way too big for us to compute. So this is actually intractable. So instead of naively looping over all possible labelings of x, we're going to use dynamic programming to compute that sum efficiently. How efficiently? Well, the faster algorithm is only going to take n times the label set size squared time. So in the previous slide, I said the naive approach took n to the label set size time. But with this faster dynamic programming approach, to compute the sum of all possible labelings of x, where the sentence length is 17 and the number of labels is 40, it requires about 27,000 steps, which can be done super fast, well under a millisecond. So how does the scoring function for CRFs actually work? Well, we're just going to multiply a bunch of potentials together. So what are potentials? Well, the simplest kind of potential, where a CRF is basically still a CRF, is a label-word triplet, which has an associated score. So to compute the score of determiner, noun, verb for the dog barks, we're going to, well, first we're going to add in a start token to the beginning. This is a really common pre-processing step. And we're going to take adjacent labels and the corresponding word, get the potential, then multiply it. So the first potential is start determiner the, which in this case has a value of 2. And we're going to multiply that by the next potential, determiner noun dog, which has a value of 3. And we're going to multiply that by the last potential, noun verb barks, which has a value of 2. And multiplying these potentials together, we would get a score of 12. So that's how the scoring function for a CRF basically works. And I just want to remark a bit on what I consider the specialness of a CRF and the unique place on the landscape of machine learning models that they hold, that I'm familiar with. With CRFs, you're explicitly modeling the interactions between output labels. So the actual stuff you're predicting interacts with each other. I've often seen this described as so-called structured prediction, where you're not just predicting labels independent of one another, but the labels you're predicting need to be cohesive and cohere together. This is pretty different from most other machine learning models that I've had experience with, like with logistic regression, for instance, where you're just predicting a single value y for a data point x. So in the last slide, we alluded to the fact that potentials are label-word triplets. So let's look at how we would store these potentials as the parameters of a CRF. We can store all the potentials in a vocabulary size, by label set size, by label set size, 3D tensor that we're going to call lambda. So for instance, for the word the score potential for it having a label of determiner and the previous label being noun is 0.5 in this case. These are essentially the parameters of a CRF that we're going to learn during the training process. So one thing I wanted to touch on a little bit was the difficulty I had in understanding the dynamic programming algorithm. I'm pretty sure this is the first dynamic programming problem I've come across where each cell in the dynamic programming table represents a sum. Usually, always, when I'm doing dynamic programming problems, it's dealing with a max. Like the DP value at cell I is the maximum length substring of the prefix of x up to I. Something like that. Which makes a lot of intuitive sense. Like if you're trying to compute the max of something, you can usually throw away most of the information along the way and just keep the maxes. And you can still get the answer. But this problem is with sums. The value of the DP table at cell ij is the sum of all label sequences of size j that end in POS tag I. And the part I was really struggling with was propagating the current DP value to get the next DP value in the table while maintaining the sum structure. So for instance, if we want to compute this DP value, alpha 2, 3, we sum up a bunch of terms from the second column, but I'm only going to look at the contribution of this term here, which is alpha 2, 2. So the contribution from this cell is alpha 2, 2 times the potential VV barks. And what this operation has to do is extend all the labeling sequences that are implicitly encoded in alpha 2, 2 that are being kept track of, and it has to preserve the structure that they're all being summed together. It can't somehow destroy that sum structure. It has to maintain that sum structure implicitly. So I was really struggling with how that works. Well, I finally figured it out, how it works. It relies on the distributive property with multiplication over addition. So for instance, let's look at how we compute the contribution of alpha 2, 2 to alpha 3, 2. So we're doing alpha 2, 2 times the potential VV barks. So what is alpha 2, 2? It's this term right here, which is a sum of all POS tag sequences of length 2 ending in V. There's noun verb, there's verb verb, and there's determiner verb. The start token is there, but I'm not focusing on it right now. Those are all the POS tag sequences of length 2 ending in V. Now, we have to extend all those sequences with the potential VV barks. And here's how we can do that. This term, VV barks, gets distributed across each of these terms and extends each sequence one step. And we still have a sum as a result. because distributing a number across a sum with multiplication preserves the sum. So just to clarify, this expression is the contribution of alpha 2, 2 for alpha 2, 3. And you can see all the sequences in alpha 2, 2 get extended one step. So with the dynamic programming algorithm to compute the denominator term of a CRF prediction, you can actually have a vectorized version of it. This was kind of mind-blowing to me because it really unifies the neural network approach where you're computing a bunch of hidden layers, which are vectors, and then you do backpropagation through them to compute gradients. In a very similar way, we compute columns of this dynamic programming table, one column at a time, to fill out the DP table using matrix multiplication, just like with neural networks. And then we'll backpropagate through these column vectors to compute gradients, just like we would with neural networks. And so here's a picture of the entire CRF model, computing the probability of determiner, noun, verb, given the dog barks. So there's two parts to this diagram. There's computing the numerator up here, and there's computing the denominator down here. The numerator portion is pretty simple. It's just looking up these triplet potentials and multiplying them together to produce the score of x and y. The denominator portion computes successive columns of the dynamic programming table, one column for each word, via matrix multiplication of the potential matrices. And then we sum up the last column, which gives us the denominator z. Then we just divide the score by z to get the probability of p. So that's how the CRF computes the probability of determiner, noun, verb given the dog barks. I just wanted to mention a few extensions to CRFs that you'll probably come across if you Google CRFs. The first one is feature functions. This allows the CRF to compute arbitrary features from the entire input. In my investigations, I decided not to focus on them because, well, I consider them an extension, and I just wanted to focus on the core of a CRF. And they also seem kind of old school, given they rely on feature engineering. I think a more modern approach that replaces feature functions are neural CRFs, which would allow you to compute a score potential for each label pair and the whole input. So you could use stuff like word embeddings combined with two labels, pipe that through a CNN, convolutional neural network, and get a score potential rather than having a single parameter for it. So for example, the input to each of these boxes, instead of just being a parameter lookup, would be the output of an entire CNN model, for instance. And during the backpropagation step, you would backpropagate all the way through into the CNN and fine-tune its parameters. In that case, the CRF really is the CNN scoring model plus the dynamic programming step to normalize the score. I wanted to demo a little bit of the code that I wrote. So the code is basically just a transcription of this diagram. Now, one thing I did extra in the code, not pictured in the diagram, is I piped each of these potentials through an exponential function. It seems like that's a really common thing to do with CRFs, so you can get positive scores along the way. But yeah, we've got the forward pass for the numerator right here. We've got the forward pass for the denominator right here. Everything is rolled into one big function. Then we do the backward pass for the numerator right here. We didn't even really discuss backpropagation, but if you're curious about it, check out Andrei Karpathy's CS 231N course, and you can learn to write backpropagation code for your model. Then we do the backward pass for the denominator. Similarly, computing gradients. And yeah, this is the forward-backward function. So it gives you the probability and the gradients of the parameters. Now, one thing that I did, which was really, really helpful with getting the forward-backward function correct, indispensable really, was having gradient checking. I kept doing this thing where I would write a bunch of lines of code for the forward and backward pass, and inevitably it would fail the gradient check every single time. It absolutely forced me to get the simplest version of this model working. I ultimately had to start with a very small subset at the very end of the model and work my way back little by little, just adding one thing at a time. It was really, really brutal, actually. Another thing that was really helpful was writing this little test code here. It basically tests the forward pass by computing the probability for every labeling sequence of x and making sure that it sums to 1, basically ensuring that the model produces a proper probability distribution. This was also a very helpful test to make sure that things were working properly. And finally, here's a little bit of training code, which trains the model and plots probabilities over time. So after every training epoch, I compute the probability for every label sequence. And what you should see here is the probability for determiner, noun, verb going up over time, and all the other probabilities going down. So yeah, determiner, noun, verb. Yeah, this one's like going up. Surprisingly, it seems pretty sensitive to the initialization of lambda and actually doesn't converge every time, which is pretty weird. So that's implementing a basic CRF in Python. I hope you enjoyed the video. If you want to chat about CRFs or have any questions about the video, feel free to hit me up, send me an email. My contact info is in the description. Bye-bye.